Let us see the relative velocity formulation first. The momentum equation contains 4 additional acceleration terms. The first two terms are the Coriolis acceleration. In the first two terms are the Coriolis acceleration, which are given by 2 omega cross Vr, and the centripetal acceleration, which is omega cross r bar. This is the centripetal acceleration term. These terms are applicable for both steadily moving reference frame and accelerating reference frame. In steadily moving reference frame, these terms are constant, while in accelerating reference frame, these terms are function of time. The third and the fourth term are due to the unsteady change of the rotational speed and linear speed. These terms vanish for constant translational and rotational speed. In addition, we also have the viscous stress, which is tau r, and this particular term is similar to the original momentum equation, except that we have used relative velocity in this. So this is tau r. So this is the new momentum equation which is obtained after transforming the inertial frame to the moving reference frame. In this, alpha term is the time rate of change of rotation velocity, and A term is the time rate of change of translation velocity. Continuity equation is also written in terms of relative velocity. Now we come to the absolute velocity formulation. In the absolute velocity formulation, the governing equation of fluid flow for steadily moving reference frame is shown here. This is the continuity equation, this is the momentum equation. In this formulation, the Coriolis and the centripetal acceleration can be further simplified into a single term, which is this particular term. This is given by omega bar cross the subtraction of V bar and Vt bar. The term is relative velocity, this particular term. There is no explicit term involving A bar, that is acceleration, translation acceleration here, since it is written in terms of absolute velocity. So this is the momentum equation for absolute velocity formulation. Till now we have studied a lot of concepts related to fundamentally what is the moving reference frame approach, what is the single moving reference frame approach, what are the equations behind it, how they are written, how the inertial reference frame equations are transformed to the moving reference frame equations. Now we are going to focus on how the single reference frame model is applied, or what are the different setup steps in Fluent in order to model the single reference frame approach. There are some mesh constraints when you are setting up a problem involving moving reference frame approach. For a two-dimensional problem, the axis of rotation must be parallel to the z-axis. For a two-dimensional axisymmetric problem, the axis of rotation must be the x-axis. For three-dimensional geometries, you should generate the mesh with a specific rotational axis in mind for the rotating cell zones. Usually it is convenient to use the x or the y or the z axis, which are the standard Cartesian axis, but ANSYS Fluent can also accommodate arbitrarily rotating rotational axis. Also, for three-dimensional rotating problems, if we want to model walls which have zero velocity in stationary frame, then these walls must be surface of revolution with respect to the axis of rotation. If the stationary walls are not surface of revolution, we must enclose the rotating parts with a interface boundary which takes our problem into multiple zones, for which there is the multiple reference frame approach or the mixing plane approach. We will see these in the coming lectures, not in this particular session. The single moving reference frame model is associated with a single fluid domain. We can also divide this domain into many connected fluid zones, but still each zone must have the same moving reference frame speed and axis. Domain usually moves with a specified reference frame and axis of rotation. We usually make constant rotational speed and no translational simplification in order to apply the SRF model. What are the different boundary conditions that we can use in the moving reference frame? We can use the standard boundary conditions of inlets, outlets, walls. Rotationally periodic boundaries can also be used. Rotationally periodic boundaries require spatial periodicity, and rotational angle should be evenly divisible into 360 degrees. There are some rules for moving reference frame shapes. Boundaries which move with the fluid domain may assume any shape. Boundaries which are stationary with respect to the laboratory or fixed frame must be surfaces of revolution. Surfaces of revolution is about the moving reference frame axis of rotation. The rule applies to both walls and flow boundaries, that is inlets as well as outlets. Let us visualize a schematic problem for the SRF problem setup or model setup. This is a typically suitable problem for SRF model. There is a hub surface which is given in red, this particular surface. There are blades, these are the blades. And a shroud and casing surface. So this is the shroud and casing surface, that is the outer surface. For this problem, we can define the x-axis as the rotating reference frame axis. And we can model this problem using the moving reference frame. We also have the inlet boundary condition and the outlet boundary condition. And the shroud and the casing surface and the inlet and outlet are surfaces of revolution. So these surfaces are surfaces of revolution as well as inlets and outlets. So this is how we divide the entire problem into a moving reference frame problem using different. So this is our moving reference frame or moving domain. Another pictorial representation in order to understand the SRF concept and setup. If we consider a rotor around which we have to model the flow which is rotating. So this is the rotor that we are going to consider, and this particular flow is basically rotating. Same case here. These are the blades of the rotor and the flow is rotating around those blades. For this, we have to select the SRF domain and model setup for considering this as a single reference frame approach or model. The first image, that is this particular image on the left, we consider a circle around the rotor which seems a correct representation, and the SRF model is applicable for this setup. So if we consider this particular circle around the flow, we can model this particular problem using the SRF approach. In the second image, which is the right image, we have an additional geometry, that is the 4 baffles. These 4 baffles are additional geometry in this particular problem. Now the problem comes with the baffle because the baffles are stationary and they are not surface of revolution. So this particular case violates the case for SRF, and we cannot use the SRF model in this particular second case. What sort of geometric setup do we need for the SRF model? We are going to see that in this particular slide. First, let us see in 2-dimensional cases. For 2-dimensional cases, the geometries we can have are geometric rotation about the x-axis. For 2D planar geometries, we can have geometric rotation about axis normal to the xy plane with a specified origin. So for 2-dimensional case, we can have such type of geometric representation. This is the x-axis, this is the x-axis, this is the y-axis, and we can consider a rotation along the z-axis, which is this particular axis of rotation. And we consider a surface which constitutes our domain, that is surface of revolution, and this is the moving domain. This is for 2D planar cases or geometries. Periodic boundaries are also permitted in this particular case for 2D axisymmetric and swirling cases, which is shown here, this particular case, axisymmetric. In that case, we can have the rotation about the x-axis. So we can construct this particular rotating domain, have these as surface of revolutions, and consider the rotation around the x-axis, which is the axis of symmetry as well.